is a CBSE AIPMT 2014 question from mechanical properties of solids. Problem says certain number of spherical drops of liquid of radius r coalesce to form a single drop of radius r and volume V. So what he's saying is there is small drops each of radius r, certain number, let that number is, let n is the number of that small drops. These n drops combine together to form a big drop of radius r, volume V. That's what he's saying. Of course, T is the surface tension of the liquid. Then how much energy is released in this process? That's a question that he is asking. So if we have to find out the energy released in the process, we have to go for the core formula, core concept actually. What is that concept tells you is surface tension is defined as work done in increasing the unit surface area of the liquid. That implies work done equal to surface tension into change in the surface area. That is A final minus A initial. This work done is stored in the format of energy, and when small drops are combined to form a big drop, energy is released in this process. Energy released is when a big drop has to split into small drops, energy is required, absorbed, but when small drops are combined to form a big drop, energy is released. How much energy is released that we have to calculate. Yeah. Then what is that A initial? Let me write these values, right? Area initially for one small drop being a spherical drop, area is 4 pi r square. Like that, there are n drops are there. So area small is 4 pi r square into n. That is area initial, initial area of the system. Area finally is when the small drops are combined into a big drop, mega radius is 4 pi r square. That implies work done in this case is surface tension into n into 4 pi r square, small r square, minus 4 pi capital R square. Be careful that I have to write the bigger area first minus smaller area. When n small drops are together, we'll have a larger area when compared with the one big drop. So we have to write that way. But this n is the number of the drops that is not given for us. But what we can say is, as all small drops are combined to form a big drop, what we can say is, the volume of all that n drops equal to volume of big drop, because density equal to mass by volume. Density is constant, mass has to be conserved, and hence volume has to be conserved. Volume of each small drop is 4 by 3 pi r cube. Like that, there are n number of drops are there. So the total volume of n drops is 4 by r cube into n. Volume of the big drop is 4 by 3 pi capital R cube. 4 by 3 pi and 4 by 3 pi can cancel. So n can be found as capital R cube by small r cube, where capital R is the radius of the big drop, small r is the radius of the small drop. Let us substitute this n value in this equation. That implies work done is equal to energy released equal to T in the place of n. Let me write capital R cube by small r cube, 4 pi small r square minus 4 pi capital R square. Now, what is in common that what we can take in all these terms is, T is of course is there, 4 pi r square is there, 4 pi and 4 pi is there. But if we have to say express it in terms of a volume of a drop, answers are in terms of volume of the big drop. V is the volume of the big drop. What's the volume of the big drop is? 4 by 3 pi r cube. So 4 is there, pi is there, r cube is there here. But by 3 is not there. So what I will do is, for each of the term, I will multiply with 3 and divide with 3, so that r cube 4 pi r square by small r cube multiplied by 3 divided by 3 minus 4 pi. Only r square is there. Multiply with 3 and divide with 3. But I need r cube, na? So I'll multiply with an r, capital R, and divide with one more capital R. So I have, see carefully, multiplied and divided with 3, multiplied and divided with r, so that our basic equation is not going to change in any way. So this can be further written as work done or energy released is T. Now I can take 4 by 3 pi capital R cube common. So what is taken out? 4 is taken out. This 3 is taken out. Capital R cube is taken out. Pi is also taken out. So what is remaining is 1 3 is there. Small r square by small r cube is small r is remaining. 3 by small r minus what is taken out here? 4 pi is taken. R square and r cube is taken out. By 3 is also taken out. So what is remaining is obviously this 3 and capital R. So this value becomes minus 3 by capital R. So the energy released is T. 4 by 3 pi r cube is volume. In this I can take 3 also common. 1 by small r minus 1 by capital R is the energy released. So my answer is, you can see this one, 3 TeV, this one, 3 TeV, and 1 by small r minus 1 by capital R is the answer for the problem. That much of the energy is released. So to solve this problem, we have used some basic concepts. We have to know carefully that basing on the very definition of surface tension, work done can be written like T into change in the area, bigger area minus smaller area. Next, as volume is consumed, we have got a relation between small n value of the n in terms of capital R and small r. And simply by substituting the values, I got the answer. I want you to go through this equations once again if required, so that you will get the clarity that is required. That's it. And thank you for watching.